All right, welcome back, everybody watching along at home. Okay, so this is section 1, 2. It's titled Mathematical Models. What we're going to get into in this section, again, all of chapter 1 is kind of like a review. In my opinion, it's a lot of review from Algebra 2. Okay? Like when I go through these problems in the notes, I'm seeing a lot of things that I could have given you on your tests and quizzes. Now, again, it's good to review them. It's good to dust the cobwebs off, but it is review. We're going to be talking today about all the different types of functions that you could see in calculus. All the different types of functions, the variety of different types of functions, and how we create those functions. Like the first thing we're going to talk about is how to take data and how to take points and things like that and create these functions. Like I'm alluding to regressions, like linear regression, quadratic regression. You could even do exponential and logarithmic regression, and even trigonometric regression if you really wanted to. And what I mean by that is putting a scatter plot on and finding where the line of best fit is. And we'll do that with our calculators. Okay, in general, like why do we need, or how do we create these models? How do we create these models? Well, a mathematical model is just a mathematical description, often by means of a function, of a real-world problem or phenomenon, such as the size of population, demand for a product, speed of falling object, concentration of a product in a chemical reaction, life expectancy, cost of emission reduction. Like you could model all sorts of things with mathematical functions. Like when back in April and May, when we kept getting all of the numbers for all of the cases and hospitalizations and ICU, and they were like updating that daily, those numbers daily. I don't know, the nerd in me just started putting it in my calculator, and I was actually graphing it as it was happening. I was trying to see the graph of how the whole pandemic was playing out. Pandemics actually follow a logistic curve. So there's different ways that you can take data, try to put a function to it, and maybe see what's happening in the future. Okay. The purpose of a model is to understand the phenomena and perhaps make predictions about it in future behavior. So you start with a problem, a real world problem. You create a mathematical model, and that mathematical model could come from data, that could come from things that we already know, like physics equations, or pi r squared, area equations, things that are already out there, different chemistry equations or whatever. You solve, you take your problem and you work the equations that you found. You make conclusions based on that, and then you interpret your results. And then in the end, you have to interpret your results in a way that, you say, okay, did it come out the way I wanted it to, or what can we tell from those results? Can we tell anything from those results? Thinking back to the regression equations that we worked with in Algebra 2, we looked at those R values and said, okay, is this a proper model to fit this data? Okay, and then we can predict based off of that. So let's talk about those. Linear models. Obviously, the most basic that we could get, the linear function. I guess the most basic would probably be constant, y equals c, y equals a number. But the next one up would be linear. When we say that y is a linear function of x, we mean that the graph of the function is a line, a straight line, no curves in a linear function. So we can use the slope-intercept form of the equation to write a formula for the function as follows. Y, or f of x, is equal to mx plus b. We've seen that a million times over, right? It's always best to put it into slope-intercept form because that's the most common. You can use point-slope form to put it into slope-intercept form if you really like to. That's kind of the method I like best. And I'll show that here in a second. So, for example, here, first example that we have. As dry air moves upward, it expands and it cools, okay, up into the atmosphere. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature, T, as a function of the height, h. It's always very important that you think about how the problem is worded, okay? And it's especially important when I talk about how you're defining the function. Express the temperature T as a function of the height h. So I know right away before reading anything else that when I create this model, okay, when I create this equation, I know it's going to be T of H. Right? That's my model. That's my equation. Temperature as a function of height. Assuming that it's a linear model. Okay, assuming that it's a linear model. And at the end, we'll talk about why it is a linear model and how we know that a linear model is appropriate. Okay, now, what we're given here is basically two pieces of data, isn't it? Okay, we're given two pieces of data. We're given a piece of data that at ground temperature, it's 20 degrees Celsius, and at height of 1 kilometer, it's 10 degrees Celsius. So really two points at 0 height, and I know I'm putting height as x because that's how I define my function. So at 0 kilometers, I've got 20 degrees Celsius. And then at a height of 1 kilometer, I have 10 degrees Celsius. Now, right from there, that's basic algebra 1. How do I create an equation given 2 points? That's exactly what we're going to do. First thing I would need to do is find the slope. The slope would be 10 minus 20 over 1 minus 0, right? Change in y over change in x. So negative 10. And now at this point, you can either choose to do point slope or solve the B method. I don't know, I like point slope, but we don't even need to do any of that because what's my y-intercept? 20, it's given to us, right? 0, 20. So my B value is 20 in this case. So I can take negative 10x plus 20. All right, so there's A. Let's talk about my domain before we move past A. What's my domain of this? Now think about it in terms of the problem that we have. 0 to infinity, I guess, right? If we really wanted to keep going, I guess scientifically we're not really sure like what's going to happen way out there. I don't know. And then my range would be all real numbers, right? Okay, and actually, my range. Well, let's talk about the graph, and then we'll talk about the range as well. All right, draw the graph of the function in part A, and what does the slope represent? All right, so let's sketch the graph. Okay, we've got height as my x, and we've got temperature as my y. Okay, we're in kilometers here, so 1, 2, 3, and actually I need to move my word height, don't I? Because I will go into the negatives. In terms of temperature. Temperature is something that can't go negative. I'll just put height out here. And I'm going to start at 20 degrees Celsius, right? So let's just make these 1, 2, 3, and so on. And let's make this 10, 20, 30. Let's make this negative 10, negative 20. Okay, that means we start here at 0, 20, and we work our way downward at 1, 10, and then at 2, 0, and then 3, negative 10. Right, so here, sorry, I drew that graph kind of poorly, so missed the dot there. So what would be my range? Sure.
Negative.
Yeah, it would stop at 20, wouldn't it? Good. Okay, what's my slope? What does the slope represent? Decreasing 10 degrees for every what? For every 1 kilometer. Okay. It's always good when you're talking about the slope, and in the homework it asks a lot of what does the slope represent? What does the y-intercept represent? When you're talking about the slope, what does the slope represent? It's a really good idea to talk about change in y over the change in x. Okay, over 1 unit of change in x, and that's usually what we have for our slope. It's usually a whole number. Okay, or it's a decimal or something like that, especially if the word counts as decimal. So you're going to say, you know, if this was maybe 10.5, down 10.5 degrees for every 1 kilometer. Okay, make sure you use both of them. And then we say, what is the temperature at a height of 2.5 kilometers? Well, obviously we would just plug that in. Finish off the blue there. We would say T of 2.5 kilometers, and that would be negative 10 times 2.5 plus 20. Okay, so negative 5 degrees. Make sense? All right, let's keep it moving. Okay, that is, you know, using 2 points, right? I was told these 2 points, 2 discrete values. If I had a whole set of values, and I am creating an equation based off of all of these sets of values, like a regression, like doing quadratic regression, doing linear regression, whatever it is. We call that using an empirical model, okay? An empirical model, which is, when you're using an empirical model, that's strictly based off data, strictly based off things that you have observed to be true, and then you're going to create a model based off of that. You are creating what's called an empirical model. You seek a curve that best fits the data in the sense that it captures the basic trend of the data point. Okay, you're looking for a trend line here. All right, so let's think back all the way to Algebra 2. Table 1 lists the average carbon dioxide level in the atmosphere measured in parts per million at Mauna Loa Observatory from 1980 to 2012. Use the data in Table 1 to find a model for the carbon dioxide level. Okay, so let's get out our calculators and do that. Okay. If you don't have a calculator today, make sure you have your calculator. But you can follow along up here. It's good to do the process, though. It's always good to refresh your memory on that. We did this with every chapter in Honors Algebra 2. Every single one. All right, so let's plug our data in. So how to do that? We go to Stat, and then we hit Edit. Okay. Remember to clear out anything that's there. Oh shoot! I just deleted my list. Darn it! Oh, stupid. Stat Setup Editor. Done. Okay. There we go. Stat Edit. You got to hit the clear button, not the delete button. Clear out anything that's there. Clear down. And now let's input the years as our x values, and then the parts per million in the CO2 level and the y value. Okay, so take a minute and do that for yourself. Should have 17 pieces of data. It's always a good idea to go back and check to make sure that you plugged everything in correctly. That would really stink if you did not plug things in correctly. So I'm just going to go through and spot check here. looks like I'm good. Right here. Okay, now to get the scatter plot, now it's on the homework. There are problems that say draw the scatter plot. I'm okay if you don't draw the scatter plot. I think we can all draw a scatter plot. I don't even think I made you do that in non-algebra 2. Okay, but you want to clear out anything that's in your y equals, and you want to make sure your plot is on. You want to make sure your plot is on. And then you hit zoom, and then stat, zoom statistic. And that'll give you your scatter plot. You can obviously see it on the screen. That was the one provided in the book. But we can see here that it looks like a linear model, right? You basically have to tell by the look of the graph what's the best fit, what the best fit is going to be. Now there's a way to do it with the R value. Remember, R values being closest to 1 are the best fit. So you could run a couple different regressions and see what's going on. But you know, if there's one out there that looks, you know, something like this, you know, that looks like a sine curve to me, right? Or a cosine, or some sort of trigonometric one, which we'll talk about in a minute. You know, it's going to be, or if there's something that looks like, you know, that looks exponential to me, right? So you have to base it on the look of the graph, see what's going on, and maybe you can tell from there. All right, now, use the data to find a model for the carbon dioxide level. So I'm going to go back out to my home screen, and I'm going to run the regression now. That's in stat, and then scroll right once to calc. And you see all of the regressions that your calculator does, starting with linear regression at number 4. So I'm going to run that regression. And there's my equation. Okay. Did I lose anybody? I did. There. Oh, you don't have the R value. You can turn your diagnostic back on by going catalog. Second 0 is catalog. And then if you just hit the D button, it'll jump to jump to D's. Scroll down to diagnostic. Diagnostic on. And then you just want to hit enter and enter. Then if you rerun it, it should be there. Okay. To graph the actual line, here you go into y equals, vars, statistics, choice 5, and then EQ. You remember the cheat sheet that Mrs. Naples and I gave out? I'm going to post that in Canvas because I still have that document. Okay, I'll post that in Canvas, and that runs through all of this stuff too. So if you graph that line, you know, there's our line of best fit. But the equation is back here. The equation is on the home screen here. So I'm gonna put this over here, and I'm gonna say, scroll down here, y equals 1.713x minus 3054.142. I don't know why I did 3 decimals out. Now, the book presents an alternate way to get that equation. Okay, a kind of a crude way. If you did not have your graphing calculators and you did not have that ability to run the regression, there is a way, and it's kind of acceptable, to take first and last point and use those 2 values to do the exact same thing that we did on the first slide. Find the slope, find the y-intercept, there's your equation, okay? Again, it's not using any of the other pieces of data. What's interesting to point out is that the book gives the equation, and I wrote it down here. The book gives, using first last, y equals 1.722 x minus 3070.86. It's rather close, isn't it? Surprisingly, it's rather close. Now, what happens if my first or last data point's messed up? Well, then your whole equation is going to be messed up, right? So it's always better if you have the ability to run a regression, run the regression. Use your calculator, okay? All right, so there's my model. I'll bring it down here. It says use the linear model in equation 2 to estimate, in example 2, to estimate the average CO2 level for 1987 and predict the level for 2020. According to this model, will the CO2 level exceed 420? When will the CO2 level exceed 420 parts per million? So there's a couple different questions going on here. First thing that I want to use, or first thing I want to answer is the 1987 question. Figure out what it's going to be at 1987, because notice that it's not in our table, right? 1987 is not in our table. It jumps to even years. So all I have to do in 1987 is say y equals 1.713 times 1987 minus 3054.142. Okay? So 1.713 times 1987, close parenthesis, minus 3054.142. 349.59. 349.59 parts per million, okay, in 1987. Next question being asked is okay, now 2020. What can we expect it to be in 2020? Well, in 2020, it would be y equals 1.713 times 2020. Second 20. Minus 3054.142. So we go to our calculators there, run the exact same equation, but now instead of the year being 1987, we use 2020. Plug that in, 406.118. Okay, parts per million. Now, there's different terms that we can use, like when you're making inferences about data, when you're finding a value that was contained within your data set, okay? Like here, 1987, it's within the parameters of what I had, right? Between 1980 and 2012. That is called interpolation, okay? When you find a piece of data outside of your data range, like 2020, it was future. I calculated 2050, that's called extrapolation. So interpolation is when you find a piece of data that was within your range of experiment, whatever you call this here. That's interpolation. Extrapolation is when you're finding a piece of data that has been outside of your range of experiment. All right, questions about that? Last thing I want to talk about is the parts per, the 420. 420 parts per million, that's the y value, right? That's the y value. So all I'm going to do here is find 420. I want to know when it's going to exceed 420. I want this value to be, I want to find the x value that's going to make it greater than 420. 1.713 x minus 3054.142. Okay? Because it's when it says when is it going to exceed, that's implying an inequality. So I would add over the 3054, 420 plus 3054.1713. 1713, no, that's the wrong number. 420 plus 3054.142, there we go. And now I'm going to divide by 1.713. 2028. 2028.104 greater than x. Oh, I'm sorry, x is greater than that. Okay, so that means in the year 2029, right? We're going for the nearest whole year, rounding up on that one. 2029, in the 2029 year. Questions about that? If we really wanted to get specific, we could say, what is 0.1 of a year and go, and get it that way. Okay, so that's a linear model, right? We can run that whole process for any type of model that we have, any type of model that we can use our calculators for, right? In our calculators, we've got linear regression, quadratic regression, cubic regression, quartic regression. Another example of a linear regression just with the order flipped. Natural log regression. We can do an exponential regression. We can do a power regression. We could do a logistic, and that's what I was using the numbers for the pandemic for. Sign regression is in there as well. So there's all sorts of different fits that you can do. The process is the exact same that we had just gone through. Okay? It's the exact same that we had just gone through. It just gives you different values for your equations. So now we're going to expand and say, okay, what other types of equations could we use? Polynomial equation is the next one out. Okay, that's when we have, the different degrees will tell you what the shape of the graph looks like. Degree being the highest value, like this is a degree of 6, right? Biggest exponent when it's ordered from least to greatest, from greatest to least, excuse me. Okay, coefficients are obviously the numbers in front. The degree of the polynomial is the highest power that you have. A polynomial degree 1 would be linear. A polynomial degree 2 would be considered quadratic, ax squared plus bx plus c. Its graph is always a parabola, okay? And you just shift that parabola around. As we will see in the next section, the parabola opens up, and then the next section is all about transformation, section 1.3 that we'll talk about. The parabola opens up if A is positive, A is negative, it's going to be a frowny face. Polynomial degree 3 would be considered a cubic. Degree 4 would be quartic. Degree 5 would be quintic. And then beyond that, you would just say 6th degree or 7th degree and so on. Remember the end behavior dance? Remember that? Remember positive, negative, those of you who had me? This is kind of what we're looking at there, right? The end behavior, stays the same with, this is the positive even, positive leading coefficient, even degree. This is the negative even, this is negative leading coefficient, even degree. This is positive. On the right side, it will go up, positive odd. So like say 2x to the 5th, it's going to go up on the right, down on the left, positive odd. Negative odd would be flipped, right? So like negative x to the 5th, negative odd, right? Left up, right down, okay? And it also, all of them will have the exact amount of bends and zeros, including multiplicities in terms of the degree. All of those things we talked about polynomials way back in Algebra 2, okay? So let's take a look here. A ball is dropped from the upper observation deck of the CN Tower, 450 meters above the ground, and its height h above the ground is recorded at 1 second intervals in this table. Find a model to fit the data and use the model to predict the time that the ball will hit the ground. So go ahead and plug in your data real quick. Because does it tell us what type of model? So we should decide what type of model. Remember to clear your list. Don't delete your list like I did before. I wish there was like an autofill. We just filled 9. Okay, spot check to make sure that your numbers are all right. you go back to your y equals, you clear out whatever was in there, make sure your plot is on, and then zoom, stat. I would say this looks parabolic. This looks like a parabola, an upside down parabola, but it looks parabolic in my opinion. Let me bring this over. Zoom stat. Zoom 9. You might have something else in. Hit zoom. You did zoom 9? Oh, hit zoom 6 and then you zoom 9. The clock's not on, I thought. Yeah. Okay. So this looks like the right half of a negative leading coefficient parabola, right? Facing downward. Okay, let's run a quadratic regression. How good is my R value? Very good, right? Very, very, very good. Now, those of you in physics, think about, isn't it your shoot? It's been a minute since I've been in physics. Don't tell me. -9. Is it -9.8 t squared plus VOT plus h? Isn't that an equation? Yeah. I think so, because this is acceleration due to gravity. This is your initial vertical velocity, and this is that's your starting height. That's why I got a 1 on the Just play more. So I believe this is a the model. Yeah. Okay. I can't remember if that's in feet or meters per second. I'm not sure. 9.8 would change. Okay. But the reason I say that is because that's quadratic, isn't it? This is a model of a falling object or any projectile motion, right? We did this in algebra 2. With the initial vertical velocity and the initial height. Remember we talked about like a rocket firing off, or a golf ball, or a football kicked from ground level. And we factored it, or we did other things to find when it would hit the ground again, right? This is kind of like the same thing. It's going to be modeled by a quadratic here. So it should make sense that it is quadratic. So our equation is y equals -4.9 x squared plus, 4.9, look at that, half of 9.8. -4.9 x squared plus 0.962 x plus, running out of room, 449.36. Guys, what should our true y-intercept be? Like if I was going for actual y-intercept, what should our y-intercept be? 450, the starting height, right? So our model got us really, really, really close to 450, didn't it? Right. So I would say that's also keying us in, and that's a pretty good model. Okay. Find a model for the data to fit the. So find a model to fit the data. Use a model to predict the time at which the ball hits the ground again. Okay. Well, how do we know when it's going to hit the ground? Find a zero. Okay. Find a zero. Let's do the quadratic formula. Let's do it. The opposite of b, 0.962, plus or minus the square root of 0.962 squared minus 4ac, all divided by 2a. 2 times -4.9, -9.8. Everybody follow me there? Just doing the quadratic formula with the equation that we got. Now I'll plug in my calculator. Okay, we got 0.962. I'm going inside the radical. 0.962 squared minus 4 times -4.9 times 449.36. Okay, that's inside the radical. I square root it. Square root it. Okay. So negative 0.962 plus or minus. Oh, I just hit Photoshop. Darn it. Make my computer slow down. 93.85. Divided by negative 9. Oh, seriously, Photoshop. Now, at this point, I can throw out the negative answer, right? I know that this will get me another negative solution somewhere over here, but I don't even want that. I'm not even going to try to calculate that. Okay? I want the only positive one that's going to happen. So you may be thinking to yourself, oh, well, then I've definitely just got to add this, right? Watch out, I'm dividing by a negative. Okay, so a positive on top will turn a negative. I need a negative on top to cancel out the negative on the bottom. So I'm going to take negative 0.962 minus 93.85 divided by negative 9.8. 9.67. Time, seconds. That's how long it's going to take to hit the ground. In our best estimation, based on this model, right? Based on this model. Okay. That was fun. Questions about that? Okay, so again, it was kind of like the same thing that we were doing with our linear function, just we're running a quadratic regression and, figuring out what we were answering a question based on what we had on there. Okay, so from here on out, we're just going to look at other types of functions. Take note of whatever you'd like to take note of. There's only like one or two more examples in the whole lesson. The rest is just talking through the different types of functions. So take notes, whatever you want to take notes of. Okay, so power functions. Power functions. This bell rings at 11, right? Okay, I'll talk about power functions and that'll be it. Power functions. There's three different types of power functions. Okay, first one is when n is an integer, meaning the exponent is an integer. Okay, positive integer. When when n equals 7, that's just saying x to the 7. Okay. And I'm not talking about a full polynomial here. I'm just talking about x to the 7, x to the 6, x to the 10. Okay. Positive integer. When it's like that, there's always going to be the y-intercept crossing at 0, 0 at the origin. Okay. The odds are going to look very similar. The evens are going to look, except for 1, obviously. The evens are going to look very similar as well. Okay. We know the shape of those graphs. We have a parabola and then the cubic equation. They will all match either x to the second or x to the third. Okay. The second type is when it's a negative integer, when it's a fraction. When it's a fraction. What happens when it's a fraction? What happens when our power is a fraction? What does that turn into? It's a root, right? Like x to the 1/2. X to the 1/2 power would be the square root. X to the 1/3, cube root. X to the 1/4, fourth root. Okay? When n is a positive integer and you have 1 over n, a is 1 over n. Okay? It's called a root function. It's called a root function, where n is the index. Okay? 1 over n, where n is the index. So like 1/3 power would be third root, 1/4 power would be fourth root. Okay. If the n value is even, if your index is even, the domain is always going to be 0 to infinity, right? No negatives, because that would bring up a non-real answer, right? Taking the square root of a negative number. If the index is odd, 3 or more, then it's all real numbers. We can take the square roots of negative numbers if it's odd. Okay, it's negative infinity or positive infinity. That would be the domain. Okay, and then the last one that we would have is a reciprocal function. A reciprocal. That's when x would be negative. Okay, that's when x would be negative. Sorry, the exponent would be negative, like x to the negative first. Okay, that would be a reciprocal. In algebra 2, we studied inverse variations. And inverse variation would be a reciprocal. Okay? We talked about that when we talked about rational functions, which is the next one that we'll talk about tomorrow. Okay? The graph looks like a hyperbola, okay, with separate parts to it, like one on the top right, one on the bottom left, if it's just the parent 1 over x. Okay. A lot of equations that you come up with in the science classes, a lot of those are inverse variations. And we have different variables in the denominator. They give the example of Boyle's law, V is equal to field of phi. So it's inversely proportional, inverse variation. All right, we'll pick up there tomorrow. Come on.